Welcome back to the deep dive. Today, we are doing something a little different.
Yeah, we are.
Usually, we're looking out at the horizon, talking about future tech, complex sociology, or, the history of big ideas. Today, we are literally grounding ourselves.
Quite literally.
We are looking down. We are talking about the stuff beneath our feet.
It is the one thing we are in contact with every second of every day, yet we probably understand it the least. It is the literal foundation of everything we know.
Exactly.
Okay.
We are diving into a stack of materials all about rock hunting, geology, and really just the secrets of the Earth. Our main guide for this journey is the DK Eyewitness Explorer, Rock and Fossil Hunter, which is this fantastic, really hands-on guide.
It's a great one. Very practical.
And I have to admit, before digging into this, I kind of thought of rocks as just rocks,
Yeah.
inert lumps of hard stuff.
That is a very common misconception. I think we all tend to see the ground as static, just a stage that we walk around on.
Right, it's just...
Up there. But the reality is so much more dynamic. The core insight from all this material is that the stage is actually alive. It's moving. It's recycling itself. It's a dynamic, violent chemical engine that just happens to operate on a timescale we can't easily see.
It really is. I mean, the phrase third rock from the sun gets thrown around a lot, but when you actually stop to unpack that,
Yeah.
we are living on a rock,
Yeah.
a massive spherical rock.
Very active rock.
And what blew my mind right off the bat is that the ground isn't just dirt. It is a massive shifting archive of history, chemistry, and physics.
And it is an archive that is constantly being rewritten. That is the key. The Earth is about, 4.5 billion years old, and it has not been sitting still that whole time. It is essentially a giant recycling machine.
A recycling machine. I love that image. It makes so much sense.
It is. It takes old rock, melts it down, presses it into new forms, pushes it up into mountains, and then wears it down into sand again. Every single stone you pick up has been on a journey that likely spans millions, if not billions, of years.
And it's not just about the past, is it? I was surprised to learn just how much rocks are part of our current daily lives. I mean, we are talking ingredients for toothpaste.
Oh, absolutely.
The filaments in light bulbs, the facing of skyscrapers, it's all rock.
It is. We are entirely dependent on the geologic world, whether we realize it or not. Every skyscraper, every computer chip, every glass of water, it's all linked to geology.
So here is our mission for this deep dive.
Mm.
We want to turn you, the listener, from a passive observer who just walks over this stuff into a rock hound.
A rock hound. I like that term. It implies an active search, a curiosity. It's not just a rock collector, it's a hound. You're on the hunt.
Exactly. We're going to unpack the architecture of the Earth itself, figure out this whole rock cycle business, learn how to identify minerals like a detective, because apparently color is a terrible way to do
It's
it.
the worst way. It's a trap.
And we'll even talk about how to find actual space dust on your roof.
Which is a real thing, and much easier than you might think.
I cannot wait to get to that part. But let's start big. Let's start with the planet itself. The source material uses a really simple but incredibly effective analogy to explain the structure of the Earth. The egg.
The egg analogy is a classic for a reason. It simplifies a very complex structure into something we can all visualize. But, we need to stress test it a bit to really get the scale. So imagine a soft-boiled egg.
Okay, I'm picturing it. Breakfast time.
Right. So right in the center, you have the yolk. That represents the core. In the Earth, this is the heaviest material. When the Earth was forming, it was just this hot, molten ball. The heavy stuff, mostly iron and nickel, sank right to the middle.
So the core is basically a giant ball of hot metal. Is it liquid or solid?
Well, both. The outer core is liquid, and it's the churning of that liquid iron that generates Earth's magnetic field. But the inner core, even though it's hotter, is solid.
How does that work? If it's hotter, shouldn't it be liquid?
It's the pressure. The pressure at the very center of the Earth is so immense that it forces the iron atoms into a solid crystal structure, even at temperatures as hot as the surface of the sun.
Wow. Okay, so yolk is the core. What's next?
Now, around that yolk, you have the white of the egg. That represents the mantle.
And this is the thickest layer, right? It's like most of the egg.
It represents the bulk of the Earth's volume, about 84% of it. But here is where the soft-boiled part of the analogy is so important. It's not solid like a brick, it's soft. It flows.
The tape describes it as churning slowly, like thick syrup.
That is a perfect description of a property called viscoelasticity. Think of it like silly putty or warm asphalt. If you hit it with a hammer, it shatters like a solid.
Okay.
But if you put a heavy weight on it and leave it for 1,000,000 years, it flows, it churns.
So it's solid on a human timescale, but it acts like a liquid on a geological timescale.
Precisely. And it's constantly moving, churning, circulating heat from the core outwards in these massive convection currents, kind of like a lava lamp in super slow motion.
And then we have the shell, the crust.
The crust. This is where we live. And compared to the rest of the planet, it is incredibly thin. If the Earth were an apple, the crust would be thinner than the apple's skin.
That's a crazy thought.
It is. It's cold, it's hardened, and it's brittle.
And because it's brittle and it's just sitting on top of that moving syrup, it cracks.
Precisely. And that right there is the fundamental concept of plate tectonics. The shell of the Earth isn't one solid piece. It's broken into these huge fragments called plates. And because the mantle underneath is moving, churning like that syrup, the plates on top are moving too.
So they're just sort of floating on top of this hot, gooey layer.
Floating and moving, yeah. About as fast as your fingernails grow, so you don't feel it, but over millions of years, it moves continents.
This is the engine that drives everything else we're going to talk about, isn't it?
It is. It is the master system. It's why we have mountains, volcanoes, earthquakes. You have these plates interacting in a few different ways.
Okay, so what happens when they pull apart?
That's called a divergent boundary. Molten rock from the mantle seeps up into the gap and pushes the plates apart. That's how we get new ocean floors. The Mid-Atlantic Ridge is a massive underwater mountain range where this is happening right now.
And then the opposite happens. They crash together.
Right. A convergent boundary. Plates crunch into each other. Usually, one plate, the denser, heavier oceanic plate, is forced down underneath the other, a process called subduction. It gets pushed back into the mantle, it heats up, it melts.
Yeah, it gets recycled.
It gets recycled. And that melting rock can then rise to the surface and create volcanoes. It's all connected.
Which brings us perfectly to the families of rocks. The source material breaks this down into three main categories, or families, and this is what they call the rock cycle.
Correct. The three great families: igneous, sedimentary, and metamorphic. And they aren't just bins to sort rocks into, they really represent stages in a life cycle. A rock isn't born one type and stays that way forever.
It can change. Okay, let's start with igneous. The source calls this fire rock.
That's literally what the word means. Igneous comes from the Latin word ignis, for fire. These are rocks that are born from heat. They form when molten rock magma or lava cools down and turns solid.
But there's a crucial difference depending on where it cools, right? This is a big aha moment for me.
A huge difference. It's all about the speed of cooling. It's the most important factor.
Okay, so walk me through it. What if it cools underground?
If that molten rock, we call it magma when it's underground, stays trapped deep in the crust and cools down very, very slowly, over thousands or even millions of years, it gives the atoms inside time to find their partners. They can arrange themselves into large, well-defined crystals.
So they have time to get organized.
Exactly. They interlock like puzzle pieces and form a coarse-grained rock. The most famous example is granite.
So I look at my granite countertop, and I can see those little speckles of black and pink and white. Those are individual crystals that grew very slowly deep inside the earth.
That's exactly what you're seeing. You are looking at a process that took an immense amount of time. It's slow-cooked rock.
Okay, so that's the slow cook method.
Yeah.
But what if it erupts? What if it comes out of a volcano as lava?
Then it cools instantly. Or, relatively instantly. Hours or days, not millions of years. It's flash frozen. The crystals don't have time to grow large.
There's no time to organize.
None at all. So you get rocks with microscopic crystals, or sometimes no crystals at all. It just cools into a volcanic glass, like obsidian. Basalt is the classic example of a fine-grained igneous rock. Most of the ocean floor is made of it.
The source mentions the Giant's Causeway in Northern Ireland as a prime example of this.
Oh, it's spectacular. It's one of the natural wonders of the world, really. About 60 million years ago, there was massive volcanic activity there. A huge, thick lake of basaltic lava pooled in a valley and started to cool.
And as it cooled, it shrank.
It contracted, exactly. But because the cooling was very uniform from the top down and the bottom up, the tension, the stress from that shrinking distributed itself evenly across the surface.
And that created a pattern.
Yes. The most efficient way for nature to relieve that stress is a crack at a 120-degree angle. And when that happens over and over, you get perfect hexagonal pillars.
So it just naturally cracks into these six-sided columns.
Thousands of them. It looks like paving stones made by giants, hence the name. But it's just the geometry of cooling basalt, physics in action.
That is igneous rock, born of fire. Now let's talk about family number 2, sedimentary. The source calls this the sandwich.
I like the sandwich, or maybe the history book.
Why the history book?
Because sedimentary rock is built up in layers, or strata. It's a record of past environments. It's made from sediments, which is just a fancy word for any loose material. Sand, mud, pebbles, and even the remains of living things like shells.
So erosion wears down mountains, rivers carry the mud and sand to a lake or the sea, and it just settles on the bottom.
Layer after layer after layer. A layer of sand from a flood, then a layer of mud in calmer times, then a layer of shells. Over millions of years, the weight of the new layers on top and the water above them compresses the stuff at the bottom. That's the first step, compaction.
It just squeezes it all together.
Squeezes the water out, packs the grains tight. But that's not enough to make a rock. You need one more step, cementation.
The glue.
The glue, exactly. Groundwater, which is full of dissolved minerals, seeps through the tiny pores between the grains of sand or mud. As it flows, it deposits these minerals, like silica or calcite, which act like a natural cement.
And that glues all the little bits together into a solid rock.
Boom, you have rock. Sand becomes sandstone, mud becomes shale, shells become limestone.
And because it happens in layers, you often see these horizontal bands. The source mentions the Vermilion Cliffs in Utah as a great visual for this.
Oh, it's a perfect example. You see these massive cliffs with big red and white stripes. You are literally looking at ancient sand dunes and ancient riverbeds, all frozen in time, stacked on top of each other.
And this is where we find fossils, right? You're not going to find a dinosaur bone in igneous rock.
Absolutely not. The lava would have incinerated it. But if an animal dies and gets buried quickly in mud or sand, its bones can be preserved in that sedimentary sandwich. That's why paleontologists are always searching in places like Utah or the Badlands of Montana.
Okay, third family. Metamorphic. The changeling.
The shapeshifter. I like that one.
Yeah.
This is rock that has been transformed. It started as something else. It could be igneous, could be sedimentary, and then it was changed.
So it didn't melt completely like igneous, and it wasn't just glued together like sedimentary. It was cooked.
It was cooked and squeezed. It happens deep underground. You take an existing rock and you subject it to intense heat from nearby magma, or insane pressure from continents colliding. Not enough to melt it back into magma, but enough to make the minerals inside unstable.
So the atoms literally rearrange themselves.
They recrystallize, they change form into denser, more stable structures that can handle the new conditions. The whole texture and composition of the rock changes.
So give me an example.
Okay, limestone, the sedimentary rock made of shells, gets cooked and crushed, and it turns into marble. The tiny calcite crystals grow and interlock into that beautiful, smooth stone.
So that's where marble comes from.
Exactly. Or shale, which is just hardened mud, gets cooked and turns into slate. The pressure aligns all the flat clay minerals, which is why slate breaks so cleanly into sheets for roofing tiles.
The source mentions that you can often spot these because they have wavy or stripy patterns.
Yes, that's called foliation. Because of the intense directional pressure, the minerals often line up in parallel bands, or the rock literally gets folded and twisted like taffy. If you see a rock that looks like it's been squashed, it's probably metamorphic.
And you find a lot of this in mountain ranges.
That's the prime location. When continents collide to build mountains, the rocks at the core of that collision zone get put through the metamorphic ringer.
So that's the cycle. Igneous comes from below, breaks down on the surface into sedimentary, gets buried and cooked into metamorphic, or melts back down into magma to start all over again.
It's a constant churn. Any rock can become any other type of rock, given enough time and the right conditions. It just happens on a timescale that makes it hard for us to see.
All right, let's zoom in. We've talked about these big rock families. But what is a rock actually made of? The source material makes a big point of clarifying the difference between a rock, a mineral, and a crystal. I feel like I use those words interchangeably, but I probably shouldn't.
You definitely shouldn't if you want to speak the language of geology. It's one of the first things you learn. Think of it this way. A rock is a fruitcake.
A fruitcake. Okay, I love where this is going.
The rock is the whole cake, right? It's
Yeah.
a mechanical mixture of different ingredients pressed together. The ingredients, the raisins, the cherries, the nuts, the flour, those are the minerals.
Okay, I follow that. The rock is the mixture. The minerals are the individual ingredients.
Exactly. So granite is a rock. It's the fruitcake. But if you look at granite closely, you see the pink bits, the white bits, the black bits. The pink is a mineral called feldspar. The white is the mineral quartz. The black is the mineral mica or hornblende.
So a mineral is a specific chemical ingredient.
Right. It's a naturally occurring, solid, inorganic meaning, not from a living thing chemical compound. It has a specific chemical formula and a defined internal structure. Salt is a mineral. Its name is halite. Ice, naturally occurring ice like in a glacier, is technically a mineral.
Which brings us to the third word, crystal.
A crystal is simply the shape that a mineral takes when it's allowed to grow freely. It's a solid where the atoms are arranged in a regular, repeating, three-dimensional pattern called a crystal lattice. And that internal pattern of atoms dictates the external shape of the crystal.
So crystals aren't just random jagged shapes. They're not just pointy rocks.
Not at all. They are incredibly orderly. They're the physical expression of atomic geometry. And the source material outlines 6 main classes of crystal symmetry. It's almost like, geometry class, but with rocks.
Yeah, I saw that. You have cubic, which is, well, cube-shaped. I guess that one's easy.
Like diamonds or salt or pyrite. Pyrite is also known as fool's gold. If you find a perfect, shiny, metallic cube in the ground, nature did that. The iron and sulfur atoms just love to stack up in a perfect grid.
Then you have hexagonal, 6-sided.
This is a famous family. Rubies, sapphires, emeralds, and snowflakes. Water is H2O. And when it freezes, the molecules arrange themselves into that classic 6-sided symmetry.
And then there are the ones that sound like wizard spells. I saw orthorhombic.
Orthorhombic. Think of a shoebox.
Okay, all right.
All right, angles, but the sides are different lengths. Topaz grows like this.
Monoclinic and triclinic. They sound less symmetrical.
They are. Monoclinic is like a shoebox that's been kicked, so it's leaning over.
Yeah.
And triclinic is the least symmetrical. It's just a jumble of flat faces with no equal sides or right angles. It's the messy room of the crystal world.
The source material suggests a really cool experiment to actually see this happening, growing your own crystals at home. And it's not just mix this and wait. It actually shows you how different minerals grow different shapes.
This is a fantastic way to understand the concept of a crystal lattice. It's so simple. You take a suet-like sugar or salt or alum from the spice aisle, and you dissolve it in hot water. You keep adding it until the water can't hold anymore. That's called a saturated solution.
And then, as it cools,
The water molecules contract, and they can't hold on to all that solid material anymore. So the atoms of the solute start to come out of the liquid and bond together. But they don't just pile up randomly. They snap into their preferred geometric pattern.
so the experiment notes that if you use Epsom salts, you get these long spikes.
Right. Magnesium sulfate naturally forms these long, needle-like prismatic crystals. It's beautiful to watch.
But if you use regular table salt, sodium chloride, you get perfect little cubes.
You get cubes. You are literally seeing the cubic atomic structure of the mineral manifesting in a jar in your kitchen. It's a fundamental property of matter.
And there's a note here about gemstones that I found fascinating. It mentions that rubies and sapphires are actually the same mineral. That can't be right.
It is, though. They are both corundum. The mineral name is corundum, which is aluminum oxide. Pure corundum is actually colorless.
So where does the color come from?
Impurities. Tiny little chemical accidents. If you add a tiny impurity of chromium into the crystal lattice as it's growing, it turns the corundum red and you get a ruby. If you add a little iron or titanium, it turns blue and you get a sapphire.
That is wild. So a ruby is just a sapphire with a different flavor shot.
Essentially, yes. It's nature adding a drop of food coloring at the atomic level.
Okay, so we know what rocks and minerals are. But let's say I'm out walking
Yeah.
and I pick something up. It's shiny, it's kind of greenish. How do I know what it is? The source says color is often misleading.
Color is the worst identifier. It's the first thing you notice, but it's the last thing a geologist trusts. Take quartz. It can be clear, pink for rose quartz, purple for amethyst, yellow for citrine, black for smoky quartz, or green. If you just go by color, you'll get it wrong half the time.
So you have to be a detective.
You have to be a detective. You have to put the rock through a series of tests to reveal its true properties.
And the first test in the book involves scratching things. The Mohs scale of hardness.
Friedrich Mohs, an Austrian mineralogist, came up with this back in 1812. It's a genius system because it's relative. A harder mineral will always scratch a softer one. So he created a simple scale from 1 to 10.
1 being the softest.
1 is talc. Like in talcum powder, it feels greasy and soft. You can scratch it with literally anything. 10 is diamond, the hardest natural substance known.
But most of us don't have a pocket full of diamonds and talc to test rocks with. The guide gives us some household equivalents, which I found really helpful. This is like the practical field guys.
Yes, this is the field kit you already own. Your fingernail is a 2.5 on the Mohs scale.
So if I can scratch rock with my fingernail, it's very soft.
Very soft. It's probably gypsum or talc or something similar.
A copper penny is a 3.5.
Right. An iron nail is about a 4.5. A piece of glass or a penknife blade is about a 5.5.
Okay, so that's a good benchmark. If it scratches glass, it's pretty hard.
It's harder than 5.5. Then you have a steel file, which is a 6.5. Quartz is a 7. So a steel file won't scratch quartz, but quartz will scratch the file.
So if I pick up a stone and I can scratch it with a knife, but I can't scratch it with a penny, I know its hardness is somewhere between 3.5 and 5.5.
Exactly. And that narrows down the list of suspects massively. You've just eliminated diamonds, rubies, and quartz, but you've also ruled out talc and gypsum. You're closing in on its identity.
Test number 2. The streak test. This sounds messy.
It can be, but it's one of the most revealing tests. You take the mineral and you scratch it on the back of an unglazed porcelain tile. You want to see the color of the powder it leaves behind.
Why is the powder different from the rock itself? Why is that more reliable?
Because the surface of a rock can be tarnished or weathered or reflecting light in a weird way because of its crystal shape. The streak shows the true intrinsic color of the mineral's chemical structure. It's much more consistent.
The example given is iron pyrite, fool's gold.
Classic example. To the naked eye, it looks like gold. It's brassy yellow and metallic. But if you do the streak test, real gold leaves a golden yellow streak. Pyrite leaves a greenish-black streak.
Dead giveaway.
Immediate bust. You're not going to be a millionaire. Hematite is another great one. It's an iron ore that looks shiny gray or black, like metal, but its streak is a deep blood red.
Hence the name hema, from the Greek for blood.
Exactly. The name is a clue to its streak, not its surface color.
Test number 3, the acid test. Now, we're not carrying around industrial acid, surely.
No. A little bottle of vinegar works just fine for this level of geology. This test is specifically for identifying one very common mineral, calcite.
And what's calcite in?
It's the main ingredient in limestone, chalk, and marble.
So what happens?
Calcite is calcium carbonate. It's a base. Vinegar is a weak acid. When they touch, they react chemically and release carbon dioxide gas. So if you drop vinegar on a rock and it fizzes and bubbles, it has calcite in it.
The source outlines a kitchen science experiment for this, using red cabbage water as a pH indicator.
Red cabbage is an amazing natural indicator. If you boil it, the water turns purple. That's neutral. If you add an acid like vinegar, it turns bright pink. If you then crush up some real chalk, which is calcite, and add it to the pink water, it neutralizes the acid and turns the water back to blue or purple.
And this connects back to how caves form, doesn't it?
It does. It's the exact same reaction, just happening over millions of years. Rainwater picks up carbon dioxide from the air and becomes a very weak acid, carbonic acid. When that slightly acidic rain falls on a landscape made of limestone, it dissolves it.
So it just eats away the rock.
Slowly, drip by drip, it eats away the rock along cracks and fractures, hollowing out massive caverns and cave systems.
Yeah.
A cave is just the result of a million-year-long acid test.
That is a great way to put it. Okay, test number 4 is the coolest one visually. Fluorescence.
The glow-in-the-dark test?
Some minerals glow under UV light. Why? What's happening?
It's quantum physics in a rock. The atoms in certain minerals have electrons that can absorb the invisible energy from UV light. This absorption excites the electrons, and they jump to a higher energy level.
Okay.
But they can't stay there. It's an unstable state, so they immediately fall back down to their normal state. When they fall, they release that extra energy as visible light of a specific color.
So it's absorbing invisible light and emitting visible light.
Exactly, and the source mentions that it's not just rare rocks. Your teeth and fingernails glow under a black light.
They do. Why?
They contain a mineral called apatite, which is fluorescent. And yes, scorpions also glow a brilliant green or blue under UV light. So if you're rock hunting in the desert at night with a black light, watch out.
Note to self, bring UV light, check for scorpions before picking up glowing rocks. Okay, let's move to something even more volatile. Volcanoes. We touched on igneous rock, but let's talk about the process, the pressure valve of the Earth.
Volcanoes are the surface expression of the Earth's internal heat engine. They are the vents for that churning mantle we talked about.
First, a quick vocab check. Magma versus lava.
Simple location difference. When the molten rock is underground, it's magma. As soon as it breaks the surface and erupts, it's called lava. Same stuff, different address.
Got it. Now, the source uses another kitchen analogy here, and I love this one, molasses.
Yes. To explain viscosity. Viscosity is simply a fluid's resistance to flow. how thick or runny it is.
So cold molasses is high viscosity. It's thick. Hot molasses is low viscosity. It's runny.
Right. And lava works the same way, but instead of just temperature, the most important factor is its chemical composition, specifically its silica content. Silica makes magma sticky.
So explain the difference between a gentle eruption and a violent one. Why is Hawaii usually a nice flowing river of fire, but Mount St. Helens in 1980 was a massive, catastrophic explosion?
It's the molasses factor. The volcanoes in Hawaii tap into magma that is very hot and has low silica content. It's runny, like hot molasses. Gas bubbles inside that magma can escape easily, like bubbles in boiling water, so the lava just pours out gently and flows for miles.
And that creates those wide, flat-looking volcanoes.
Exactly. It creates shield volcanoes. They're built up layer by layer of these runny lava flows, so they end up being very broad with gently sloping sides, like a warrior's shield laid on the ground.
Okay, so what about the explosive ones?
Now, take a volcano like Mount St. Helens. The magma there is cooler and has a very high silica content. It's thick. It's sticky. It's like cold, thick peanut butter. It doesn't flow. It plugs up the volcanic vents like a cork in a champagne bottle.
And the pressure from the gas below just builds and builds.
The pressure builds to incredible levels because the gas bubbles are trapped in that thick, viscous sludge. Eventually, boom, it blasts the plug out. The sudden drop in pressure causes the trapped gas to expand instantly and violently, shattering the magma into tiny bits of ash and rock that are blasted miles into the atmosphere.
And that's what creates those classic steep-sided cone volcanoes.
Yes, the iconic stratovolcanoes are built from layers of sticky lava flows, alternating with layers of ash and rubble from those explosive eruptions.
The book has the classic vinegar and baking soda volcano experiment, but it explains that the violence is all about the gas bubbles.
It's like shaking a soda can. The dissolved CO2 is the gas. When you open it, the pressure drops and the gas comes rushing out. Now imagine if the soda was as thick as cement. The can would explode.
One feature of those runny shield volcanoes like in Hawaii are lava tubes. The text describes being able to walk through them.
These are nature's pipelines. They are absolutely incredible. So a river of runny lava flows down the hill. The air cools the top layer and the sides, and they form a solid crust. It's like a skin forming on a bowl of hot pudding.
But the lava inside is still hot and liquid.
The crust insulates it incredibly efficiently. It's like a ceramic pipe. So the lava inside stays molten and keeps flowing, tunneling its way down the mountain for miles. Eventually, the eruption stops and the source of the lava drains away, but the tunnel, the solid crust, remains.
And you're left with a hollow tube of rock that you can walk through.
A perfect natural tunnel. It's literally a frozen river of fire. It's an eerie and amazing experience to stand inside one.
Okay, let's pivot from fire to, well, to dead things. Fossils.
The record of ancient life preserved in stone.
So, definitions first. A fossil isn't usually the actual bone or shell, is it?
Very, very rarely. In most cases, a fossil is a relic. It's what happens when a living thing dies and gets buried in sediment quickly, in a river or at the bottom of a lake, before it can rot away or be eaten.
Then what happens to it down there in the mud?
Over millions of years, groundwater full of those dissolved minerals we talked about seeps through the sediment. It slowly dissolves the original organic material, the bone or the shell, and replaces it, atom by atom, with a stable mineral like calcite or silica.
So a dinosaur skeleton in a museum is basically a rock statue of a skeleton.
That is a perfect way to describe it. It's a mineral replica that has preserved the exact shape and structure of the original bone. Sometimes you also get impressions like footprints in mud that hardens into rock. Those are called trace fossils.
The source material has a section on fake fossils. It warns us about commercial fakes being the big problem.
Oh, it's a big industry. People will cast replicas in plaster or resin, or sometimes they'll even carve a piece of limestone to make it look like it has a trilobite or an ammonite in it.
So how do you spot a fake?
If a fossil looks too perfect, or if it's painted, or if you see a whole bunch of them for sale that look identical, be skeptical. The book also suggests making your own fossil mud pie to understand the process.
Right, using plaster of Paris to fill a mold you make in clay.
It's a great way to see how trace fossils work like footprints. You make a print in clay, that's the mold, you fill it with plaster, and you have a perfect cast of the footprint.
We mentioned caves earlier with the acid test dissolving limestone, but the source also talks about stalactites and stalagmites.
The icicles of the cave world.
How do they form? What's the process there?
It's basically the reverse of the acid eating the rock. The water dripping through the cave roof has picked up dissolved calcite on its way down. When a drop of that water hangs from the ceiling and hits the air in the cave, it releases a little bit of its carbon dioxide.
And that causes the mineral to come out of the water.
It causes a tiny microscopic ring of calcite to be deposited. The next drip does the same thing. Drip, deposit, drip, deposit.
And over thousands of years, those rings build down from the ceiling into a stalactite.
Exactly. And if the water drips all the way to the floor and deposits its calcite there, it builds up into a stalagmite. One way to remember it is stalactites hold on tight to the ceiling, and stalagmites might one day reach the ceiling.
And there's a simulation for this in the book using Epsom salts and string.
Yes. You put 2 jars of saturated Epsom salt solution next to each other, you drape a piece of string between them with a sag in the middle, and the water travels up the string via capillary action. It drips in the middle, and as it evaporates, it leaves crystals behind. You can grow a mini stalactite in just a few days instead of a few thousand years.
I love how this book scales down geological time to kitchen time.
It's the only way to really grasp these immense timescales.
Okay, this next section is arguably my favorite. We've looked down, we've looked in caves, we've looked at volcanoes. Now we look up, or rather, at what falls from up there. Space rocks.
The sky is falling literally all the time.
The stat here is crazy. Earth is hit by something like 500 tons of space dust and rock every single day.
Most of it is just dust, particles we call micrometeorites.
So let's get the definition straight. A shooting star.
That's not a star at all. That's a piece of debris, usually the size of a grain of sand or a pebble, burning up as it hits our atmosphere at incredible speed. It's the flash of light from the friction.
A meteorite.
That's the rock if it's big enough to actually survive that fiery passage and hit the ground.
And micrometeorites.
These are the tiny particles, smaller than a millimeter, that are so small and light they slow down in the upper atmosphere without burning up completely. They just drift down like cosmic dust.
And the book claims we can actually find these in our backyard.
You can, and it's surprisingly easy. All you really need is a strong magnet.
Because many asteroids where this stuff comes from have cores made of iron and nickel.
Exactly. They are the remnants of planet formation. So here is the method from the book. You take a paper cup. You put a strong magnet, like a neodymium magnet, inside it.
Okay.
Magnet in a cup.
Go outside to a place where rainwater collects and sediments gather, like at the bottom of a downspout from your roof.
Yeah.
Your roof acts like a giant catcher's mitt for this space dust. The rain then washes it all down to one spot.
So you drag the cup through the dirt and sediment.
Drag the cup over the dry ground near the downspout. The magnet inside will attract any magnetic particles right through the paper of the cup.
Then you take it inside.
You hold the cup over a clean piece of white paper, you pull the magnet out of the cup, and all the magnetic dust it collected falls onto the paper.
And then you look at it under a microscope. What are we looking for? Because there's plenty of rusty metal junk on Earth.
That's the key. You are looking for perfect little spheres, tiny, shiny black or silver balls.
Why spheres? Why that specific shape? Because when these particles entered the atmosphere at high speed, they melted. And liquids in free fall or a vacuum naturally form spheres due to surface tension. Then they cooled and solidified in that shape. If you see a jagged, rusty piece of metal, it's probably just from your gutters. If you see a perfect tiny sphere, that is very likely a piece of an asteroid that is 4.5 billion years old.
That is just finding a piece of the early solar system in your gutter. That's absolutely incredible.
It completely makes you look at dirt very differently, doesn't it?
It really does. Moving on to section 7, rocks in human history. We obviously drilled with this stuff. But the source material highlights some really specific examples of recycled rock in famous architecture.
We have always used what was geologically available, and sometimes we've gone to incredible lengths to get the right rock. Take the pyramids in Egypt.
The book says they're made of nummulitic limestone. What is that?
Which is fascinating. It's a type of limestone, but it's made almost entirely of fossils. Tiny coin-shaped shells of single-celled marine organisms called nummulites that lived in the Tethys Sea about 50 million years ago.
So the Great Pyramids are basically giant monumental piles of ancient seashells.
It's cemented together by nature and then cut into blocks by humans, yes.
Then there's Stonehenge. That's another level of effort.
The mystery of the bluestones. They're made of a type of igneous rock called dolerite. But the specific geological signature of that dolerite comes from only one place, the Presley Hills in Wales.
Which is, what, 155 miles away from Stonehenge?
Right. So the current thinking is that Neolithic people, 5,000 years ago, somehow quarried and dragged these massive stones, some weighing 4 tons, 155 miles.
That's unbelievable dedication to your rock choice.
It shows that specific rocks had specific meanings or value. They didn't just use the local sandstone for the important parts.
What about the Taj Mahal?
A masterpiece of metamorphic rock. It's made of brilliant white marble from Makrana in India. Marble is, of course, limestone that's been purified by heat and pressure, and it's inlaid with 28 different types of precious and semi-precious stones. Sapphires, jade, crystal, turquoise. It's a jewelry box you can walk inside.
And the Empire State Building. Closer to home.
Limestone and granite facing. Classic, durable, beautiful American rock. We are still doing the same thing the Egyptians were doing, stacking rocks to reach the sky. We just have steel skeletons inside now.
But it's not just big buildings. The book has a hidden minerals in the home quiz. This was really eye-opening.
We use minerals in thousands of ways we don't expect.
Okay, let's run through a few. Pencils. What's in the lead?
It's not lead, thank goodness. It's the mineral graphite, which is a form of pure carbon, just like diamond. It's mixed with clay to control how hard or soft the pencil writes.
Toothpaste. You mentioned that earlier.
It often contains talc, the softest mineral on the Mohs scale, as a thickener, or mild abrasives like calcite or silica to scrub your teeth. You are literally brushing your teeth with finely crushed rock.
Light bulbs.
The tiny filament in the old incandescent ones is made of tungsten. That's a metal with an incredibly high melting point extracted from minerals like wolframite.
Salt. That's an easy one.
Halite. Pure mineral. It grows in cubic crystals.
What about my phone or computer?
The brain of every electronic device is the silicon chip. And silicon is purified from the mineral quartz, which is basically sand. Your computer's brain is made of hyper-purified processed sand.
It's everywhere. We literally cannot function without rocks and minerals.
We are a Stone Age civilization. We just got really, really good at polishing and manipulating the stones.
So we've hopefully convinced you, the listener, to go out and look. Section 8 is about the Rockhounds Toolkit. What do we need? It's not a lot, is it?
You don't need much to get started. You don't need a laser scanner or a geochemistry lab.
Sturdy boots.
Essential. Ankles are vulnerable on loose rock. Good traction is key.
Our hat.
A very good idea if you are near cliffs or in a quarry. Gravity works and rocks fall.
And safety goggles.
Absolutely crucial if you're going to use a hammer. Rock splinters are sharp like glass and they fly at high speed. Protect your eyes.
What about identifying tools?
The single most important tool is a hand lens. A little magnifying glass, usually 10 times magnification. It lets you see the individual grains. Is it sand? Is it interlocking crystals? You need to get close.
And a notebook and a pen.
This is the scientist's best friend. Record the location and date immediately. Don't tell yourself, oh, I'll remember where I found this. You won't, I promise.
Now, where do we look? The source distinguishes between outcrops and deposits.
An outcrop is where the solid bedrock sticks out of the ground. Think cliffs, road cuts, quarries. This is the rock in its original place, in situ. A deposit is where nature has moved the rocks for you. Riverbeds, beaches, glacial moraines.
Riverbeds sound like a good place to start.
They are great because the water acts like a natural rock tumbler. It washes the stones clean and polishes them, and it gathers a huge variety of rocks from all the upstream sources into one convenient place. It's a geological buffet.
Finally, let's talk about the code.
Yeah.
The ethics. There are rules.
Geology has a code of conduct. It's very important.
Rule 1, safety first.
Always. Know the area, watch the tides if you're on a beach, don't climb unstable cliffs, and be careful with any chemicals. We mentioned vinegar, but some people use stronger acids. Be smart.
Rule 2, respect property and nature.
Ask permission before going onto private land. It's just common courtesy. Close gates behind you. And here's a big one. Do not hammer on walls, buildings, or monuments.
Yeah, don't sample the local church wall.
Please don't. And generally, try to collect from loose rocks, rubble, or scree that's already fallen, rather than hammering into a solid, pristine cliff face. Leave the outcrop for others to see and enjoy.
And the book mentions some minerals are actually toxic.
Some are. Bright green malachite contains copper. The bright yellow and orange minerals often contain arsenic or sulfur. Cinnabar contains mercury. The rule is simple. Wash your hands after handling rocks. And never, ever put rocks in your mouth to test them.
There goes my plan to taste test the geology.
Licking a rock to see its texture better is an old geologist trick.
Okay.
But maybe stick to the hand lens until you know what you're dealing with.
Good advice. And once you find them and bring them home, Labeling.
Labeling is everything. A little dab of white correction fluid on the rock, write a number on it with a fine pen. Then you make an index card with that number and all the details. What you think it is, where you found it, when you found it. If you don't label it, it's just a rock. If you label it, it's a scientific specimen.
That distinction turns a pile of stones into a real collection.
It does. It gives it context and meaning.
So we've traveled from the iron core of the Earth through the churning mantle, watched lava cool into basalt pillars, seen mountains ground down into sand, hunted for fool's gold with a porcelain tile, and even caught a falling star in a paper cup.
It's a pretty comprehensive tour of our planet.
What's the big takeaway for you from all this?
For me, it's that geology isn't a static subject. It's not about dusty old rocks sitting on a shelf. It's about immense forces and unimaginable timescales. It's about a dynamic, living planet that is constantly destroying and creating itself. And we are just riding on the very thin, fragile crust for a very brief moment.
And we are using that deep history to build our present and our future. Every time I pick up a pencil or walk past a stone building now, I'm going to think about where that material came from, what its story is.
That's the goal, to see the world with geological eyes.
Here is a final thought for you listening. Think about the rock cycle in terms of deep time.
Really?
We talked about how concrete is just recycled rock. But think about this, the iron in the hemoglobin in your blood. That allows you to breathe. That iron was forged in the heart of a dying star billions of years ago. It became part of the dust cloud that formed our solar system, and it was incorporated into the Earth's core and mantle.
It's all connected.
We aren't just living on the rock. In a very real chemical way, we are the rock. We are part of the cycle. We are interacting with geologic and cosmic history with every single breath we take.
That's a beautiful way to put it.
So next time you go outside, just look down, pick up a stone. Don't just see a gray lump. Ask it a question. Is it igneous? Sedimentary? Is it a piece of an ancient mountain? Is it a piece of a star? You won't know until you really truly look.
Happy hunting.
Thanks for diving in with us. We'll see you next time.